Welcome engineers to Module 13, LLMOps and Deployment. In this module, we will bridge the critical gap between a working LLM prototype on your local machine and a robust, scalable, and secure AI service running in production. This isn't just about making your code run, it's about making it run reliably, efficiently, and safely for millions of users. We are going to tackle the real-world challenges that emerge when you take an LLM from concept to a mission-critical application. This is where the rubber meets the road, where theoretical models face the harsh realities of latency, cost, security, and user expectations. Get ready to build systems that not only perform well, but also withstand the pressures of enterprise-grade deployment. Let me begin with a cautionary tale that underscores the absolute necessity of robust LLMOps practices. Imagine a scenario. A small, eager team, late on a Friday afternoon, deploys their brilliant new LLM-powered feature. It works flawlessly in testing. They push it to production, eager for the weekend. By Monday morning, they are greeted not with accolades, but with a support ticket storm, and more critically, a bill from their LLM provider exceeding $50,000 for a single weekend. What happened? A critical oversight. They forgot to implement rate limiting. A malicious bot, or perhaps just an overly enthusiastic user, hit their unrate limited endpoint thousands of times per second, triggering countless expensive LLM calls. This isn't a hypothetical horror story. It's a real incident that happens to at least one team every month. The consequences are immediate: budget overruns, service degradation, and a massive hit to team morale and credibility. This highlights why LLMOps isn't merely a nice-to-have, it is a fundamental pillar of responsible AI development. We must build systems that are not only functional, but also resilient against unexpected loads and malicious intent. In this module, we will explore the critical safeguards and deployment strategies that prevent such catastrophic failures, ensuring your LLM applications are production-ready and cost-controlled from day one. With that sobering example in mind, let's now transition into Act 2, the understanding. Here, we will systematically dissect the core concepts of LLMOps. We'll explore the fundamental differences between deploying traditional software and LLM-powered applications, identify the unique failure modes of generative AI, and lay the conceptual groundwork for building resilient and efficient production systems. Understanding the why behind each LLMOps component is crucial before we dive into the how. We'll examine the complete lifecycle of an LLM request from its initial entry point to the final user response, identifying critical control points and safeguards. This act is about building a robust mental model for managing AI in the real world. Let's begin by visualizing the journey of a request through a robust production LLM system. This diagram illustrates the sequential flow, highlighting each critical layer. A client request doesn't directly hit your LLM. Instead, it first encounters a rate limiter. This component, whether global or per user, is your first line of defense against abuse and cost explosions. If the request passes the rate limit, it then proceeds to a cache check. Here, we determine if we've seen this exact query or a semantically similar one before. If so, we can return a cached response, saving both latency and cost. If not, the request moves to input guardrails. These are pre-LLM filters designed to catch prompt injections, PIL leakage, or unsafe content before it even reaches the expensive model. Only after clearing these hurdles does the request finally invoke the LLM. Once the LLM generates a response, it's subjected to output guardrails. This post-LLM filtering ensures the response is safe, adheres to desired formats, and meets quality standards before it is finally returned to the client. Each of these layers is non-negotiable in a production environment. Skipping even one can lead to the kinds of incidents we discussed earlier: cost over and security vulnerabilities or degraded user experience. This layered approach ensures resilience, cost efficiency, and safety, forming the backbone of any enterprise-grade LLM deployment. Now, you might be thinking, we already have DevOps, why do we need LLMOps? And that's a valid question. The reason we need a specialized approach for LLMOps lies in the unique and often unpredictable failure modes of large language models, which traditional software engineering doesn't fully address. Unlike deterministic code, LLMs can exhibit phenomena like hallucinations, where they confidently present false information as fact. This isn't a bug in the traditional sense. It's an inherent characteristic of generative models that requires specific mitigation strategies. Then there's the issue of cost explosions. A simple loop in your code won't incur a per token charge, but an unoptimized or unrate limited LLM call can quickly rack up massive bills, as we saw in our opening story.
Prompt injection attacks are another unique security vector, where malicious inputs can hijack the LLM's behavior or extract sensitive information. Furthermore, latency spikes are common. LLM providers can experience fluctuating response times, sometimes increasing by 5x or 10x in a single day, which necessitates robust rate limiting and fallbacks. Finally, quality degradation can occur subtly over time as models drift or user prompts change, requiring continuous monitoring and evaluation. These are not merely bugs to be fixed, they are systemic challenges inherent to working with probabilistic black box models. LLMOps is about building the engineering scaffolding around these powerful yet volatile systems to make them predictable, reliable, and safe in production. Just as DevOps revolutionized software delivery, LLMOps defines a continuous lifecycle for AI applications. It's not a one-time deployment, it's an ongoing process that ensures the health and performance of your LLM system. The cycle typically begins with experimentation and development, where we prototype models and prompts. This moves into evaluation and testing, a crucial phase where we rigorously assess model quality, robustness, and safety against various benchmarks and adversarial prompts. Once validated, we enter deployment, where the LLM service is containerized and exposed via an API, incorporating all the safeguards we'll discuss. Post-deployment monitoring and observability become paramount. We track key metrics like latency, error rates, token usage, and user satisfaction, often with specialized LLM-aware tools. This monitoring feeds directly into feedback and refinement, where insights from production inform prompt engineering, fine-tuning, or even model selection.
This continuous loop allows us to adapt to changing user behavior, mitigate new risks, and optimize performance and cost. Unlike traditional software, where a deployed binary might remain static for months, LLM systems are living entities that require constant attention and iterative improvement. The LLMOps lifecycle is our framework for managing this dynamic reality, ensuring our AI applications remain effective and responsible over time. To combat the unique challenges we've outlined, we introduce the LLM Ship It checklist. This isn't just a list of tasks, it's a comprehensive framework designed to prevent the most common and catastrophic failures of production LLM systems. Think of it as your final guardian before releasing your AI into the wild. The checklist covers 5 critical pillars: security, addressing prompt injection, data privacy, and access control; cost control, implementing strategies like rate limiting and caching to manage expensive API calls; reliability, ensuring your service remains available and performs consistently even when external LLM providers have issues through mechanisms like timeouts and fallbacks; quality, maintaining the accuracy, relevance, and safety of LLM outputs over time, requiring continuous evaluation and guardrails; and finally, observability, which provides the necessary visibility into your system's performance, usage, and any emerging issues. Each item on this checklist exists because someone somewhere learned it's important the hard way. By systematically addressing these areas, we can significantly de-risk our LLM deployments, transform a fragile prototype into a robust product, and avoid those infamous $50,000 weekend bills. This checklist will be our guiding principle throughout the build phase, ensuring we cover all bases for a truly production-ready AI application. Now that we have a solid conceptual foundation and understand the why behind LLMOps, it's time to transition into Act 3, the build. This is where we roll up our sleeves and translate these concepts into tangible code. We will construct a production-grade LLM API using Fast API, containerize it with Docker, and systematically integrate the essential safeguards we've discussed. We'll implement rate limiting to protect our wallet and service, deploy caching mechanisms to boost performance and reduce costs, and build robust input and output guardrails to ensure safety and quality. Each step will involve line-by-line code explanations, demonstrating how these critical components are woven into the fabric of a real-world LLM application. Our goal here is not just to write code, but to engineer resilient systems that can stand up to the demands of production at scale. Let's start building. We begin our build by establishing the code of our LLM service using Fast API, a modern, fast, high-performance web framework for building APIs with Python 3.7+, based on standard Python typeends. On line 1, we import Fast API, which will be the foundation of our web application. We also import HTTP exception for handling errors gracefully and depends for dependency injection, which is crucial for modularizing our security and utility functions. Line 2 brings in COS middleware, essential for enabling cross-origin resource sharing, allowing our front-end applications to interact with this API securely from different domains. This is a common requirement in modern web architectures. Line 3 imports base model from Pydantic, which we will use to define clear, validated request and response data structures, ensuring type safety and automatic data validation for incoming payloads. Finally, on line 4, we import OpenAI. This client library will be our interface to interact with the actual large language model, whether it's OpenAI's own services or an API-compatible local model. Together, these imports lay the groundwork for a robust, type-safe, and performant API. Fast API's asynchronous capabilities make it an excellent choice for I/O-bound operations like calling external LLMs, ensuring that our server can handle multiple requests concurrently without blocking. This setup provides a clean, well-structured starting point for our production LLM application, ready to be extended with further LLMOps features.
Once our fast API application is developed, the next critical step for production deployment is containerization using Docker. This ensures that our application runs in a consistent, isolated environment, regardless of where it's deployed, from a developer's laptop to a staging server or a production Kubernetes cluster. On line 1, we specify our base image from Python 3.11 Slim. We choose a slim Python image to minimize the container size, which improves deployment speed and reduces the attack surface. It's crucial for efficiency in production. Line 3 sets our working directory inside the container to /app. This is where all our application code will reside, providing a clean and predictable structure. Line 4 then copies our requirements.txt file into this /app directory. This file lists all our backend dependencies for our fast API application, such as fast API, UVCon, OpenAI, and Pydantic. By copying requirements.txt file first and then installing dependencies in a separate layer, Docker can cache this layer. If only our application code changes but the dependencies remain the same, Docker won't need to reinstall everything, significantly speeding up build times. This Docker file is a fundamental piece of our LLMOps puzzle, enabling reproducible builds and simplified deployment workflows. It abstracts away environmental differences, ensuring that it works on my machine translates reliably to it works in production. This consistency is paramount for reliable LLM operations at scale. Following our discussion of the $50,000 weekend bill, it should be clear why rate limiting is not just a feature, but an indispensable safety net for any production LLM application. Its primary purpose is to control the volume of requests hitting your API and by extension the underlying LLM provider. Without it, you are vulnerable to several critical issues: cost explosions, as every LLM call incurs a charge; service degradation, where a flood of requests can overwhelm your API or the LLM provider, leading to slow responses or outages for legitimate users; and abuse or denial of service attacks, where malicious actors can intentionally exhaust your resources. We need to implement both per user rate limiting to prevent any single user or client from monopolizing resources, and global rate limiting to protect the entire system from overall overload. Implementing this early in the request pipeline before any expensive operations is crucial. It acts as a bouncer at the entrance of your club, ensuring that only a manageable number of guests enter at any given time.
This proactive measure safeguards your infrastructure, protects your budget, and maintains a fair and reliable service for all your users. Let's look at how we can implement a basic token bucket rate limiter to achieve this essential protection. Let's implement a simple yet effective token bucket rate limiter directly within our Fast API application. This example demonstrates how we can protect our endpoints from excessive requests. On line 1, we import request from Fast API, which allows us to access details about the incoming HTTP request, such as the client's IP address or an API key, which can be used to identify individual users for per user rate limiting. Lines 2 and 3 import default dictionary and time respectively. Default dictionary is useful for initializing a dictionary with default values, and time is critical for tracking timestamps to manage the rate limiting logic. Our token buckets dictionary, initialized on line 6, will store the current state of each user's token bucket, typically keyed by their IP address or API key. The rate limit tokens and rate limit period constants on line 7 to 8 define our rate limit policy. For instance, 10 tokens requests per 60 seconds. The rate limiter function itself, which would be used as a Fast API dependency, checks if a user has sufficient tokens. If they do, their token count is decremented and the request proceeds. If not, an HTTP exception with a 429 status code, too many requests, is raised, blocking the request before it can hit the LLM. This simple implementation provides a crucial layer of protection, preventing the kind of abuse that leads to exorbitant bills and service instability. In a real-world scenario, you might use a distributed cache like Redis to store token buckets for multi-instance deployments. After rate limiting, caching is your next best friend for optimizing LLM applications in production. The reason is twofold: cost reduction and performance improvement. Every call to an external LLM provider costs money and adds latency. If a user asks the same question or a very similar one multiple times, there's no reason to pay for a new LLM inference each time. By caching responses, we can serve frequently requested content instantly and at zero additional cost after the initial call. There are two primary types of caching relevant to LLMs: exact match caching and semantic caching. Exact match caching is straightforward. If the input prompt is exactly the same as a previously seen prompt, we return the stored response. This is highly effective for deterministic queries where temperature equals 0 and for common repetitive questions. Semantic caching, on the other hand, is more sophisticated. It uses embeddings to determine if a new query is semantically similar to a cached query. If the semantic similarity is above a certain threshold, we can return the cached response, even if the phrasing is slightly different. This is incredibly powerful for paraphrased questions or variations of the same intent. Implementing caching correctly can drastically reduce your LLM API bill and significantly improve the responsiveness of your application, making it a critical component of a cost-effective and performant LLMOps strategy. Let's look at how we conceptually implement both exact match and semantic caching.
This code snippet illustrates the fundamental idea behind these two powerful optimization techniques. On lines 1 to 3, we define the concept of an exact match cache. This is the simpler of the two. It operates on the principle that if the input to the LLM is exactly the same as a previous input and the LLM's behavior is deterministic, that is temperature equals 0, then the output will also be identical. We simply store the input-output pair in a dictionary or a key value store like Redis. When a new request comes in, we perform a quick lookup. If a match is found, we return the cache response immediately, completely bypassing the LLM call. This saves both time and money for repetitive queries. Moving on to lines 6 to 8, we introduce the concept of a semantic cache. This is a more advanced technique where instead of looking for an exact string match, we look for meaningful similarity. We achieve this by converting both the incoming query and our cached queries into numerical vector embeddings. Then we calculate the similarity cosine similarity example between the new query's embedding and all cached embeddings. If a sufficiently similar cached query is found, its associated response is returned. While more complex to implement, often involving a vector database, semantic caching is incredibly powerful for handling paraphrased questions, typos, or slight variations in user input, further maximizing our cache hit rate and drastically improving efficiency. These caching layers are strategically placed after rate limiting but before the LLM call in our production pipeline. Even with rate limiting and caching in place, our LLM application isn't truly production ready without robust guardrails. Guardrails are essentially a set of rules, filters, and validation steps designed to ensure the safety, quality, and ethical behavior of our LLM system. They act as a critical control layer, mitigating the unique risks associated with generative AI. We primarily categorize them into two types: input guardrails and output guardrails. Input guardrails are applied before the prompt is sent to the LLM. Their purpose is to prevent harmful, malicious, or inappropriate content from even reaching the model. This includes filtering for personally identifiable information, PII, to protect user data, detecting prompt injection attempts to prevent hijacking, and checking for length constraints or irrelevant topics. By blocking problematic inputs early, we save LLM inference costs and prevent the model from generating undesirable content. Output guardrails, conversely, are applied after the LLM has generated a response but before it's returned to the user. These ensure the LLM's output adheres to our safety, quality, and formatting requirements. This might involve checking for unsafe content, validating JSON formats, ensuring responses are on topic, or even filtering out hallucinations. Together, these guardrails form a powerful defense mechanism, preventing our LLM from being misused, reducing the risk of generating harmful or incorrect information, and maintaining the overall integrity and trustworthiness of our AI application. They are crucial for building responsible AI systems that align with our ethical guidelines and business requirements. Let's examine how we can implement foundational input and output guardrails in Python. This code demonstrates simple checks that in a production system would be powered by more sophisticated libraries or dedicated services.
On lines 1 to 3, we define input guardrails, a function that takes a user's message and determines if it's safe to proceed to the LLM. The function returns a boolean indicating safety and a reason if blocked. Within this function, on lines 6 to 8, we have a basic PII detection check. Here, we are looking for common patterns like email addresses or phone numbers. In a real-world scenario, you would integrate a dedicated PII detection and redaction library, as simple regex can be insufficient. Further down, you might add checks for keywords associated with prompt injection or unsafe content. Now, turning our attention to output guardrails, starting around line 15, assuming a fuller code block, this function would similarly take the LLM's generated response and validate its content. For example, it could check if the response contains any disallowed topics, ensure it adheres to a specific format like JSON, or even run it through a separate smaller classifier model for safety moderation. The example code snippet primarily focuses on input guardrails, but the principle is identical for output. Define clear rules and block or modify responses that violate them. These functions would be integrated into our fast API pipeline, with input guardrails called immediately after caching and output guardrails called just before sending the final response back to the user. This dual-layered approach provides comprehensive protection, ensuring both the integrity of our prompts and the safety of our LLM's outputs. We have now systematically built the foundational components of a production-ready LLM application. From setting up our fast API service and containerizing it with Docker to implementing critical safeguards like rate limiting, caching, and guardrails, we've covered a significant amount of ground. Now, in Act 4, the Mastery, we will consolidate our learning. We'll revisit the LLM Ship-It checklist as a comprehensive summary of best practices, ensuring you have a clear, actionable framework for your own projects. We will also equip you with the one-liner knowledge crucial for technical interviews and discuss real-world examples of LLMOps in action. This final act is about cementing your understanding and preparing you to confidently deploy and manage LLM systems in any enterprise environment. Let's synthesize our knowledge and prepare for true mastery.
Let's summarize our journey with the LLM Ship It checklist, which serves as your blueprint for deploying robust LLM applications. First, rate limiting is non-negotiable. Implement both per user and global limits at the very first layer of your API before any feature code executes. This is your primary defense against cost overruns and service abuse. Second, cache everything you can. Utilize exact match caching for deterministic queries and semantic caching for similar paraphrased inputs. Caching dramatically reduces latency and LLM API costs. Third, guardrails on both sides. Implement input guardrails to filter PII, detect prompt injections, and validate input content before the LLM call. Complement these with output guardrails to ensure LLM responses are safe, formatted correctly, and of high quality before they reach the user. Fourth, timeouts and fallbacks are essential for reliability. LLM providers can experience outages or latency spikes. Your system must gracefully handle these with retries, exponential backoffs, and potentially fallback models or static responses. Fifth, the Ship It checklist prevents the top 5 failure modes: cost explosions, latency spikes, quality degradation, security vulnerabilities, and availability issues. Adhering to this checklist proactively addresses these common pitfalls. Sixth, set budget alerts before scaling. Configure spending caps and alerts at your LLM provider and cloud accounts for $50,000 to $100,000 thresholds. This provides early warning signs of unexpected costs. Finally, log everything except PII. Comprehensive observability is crucial. Log requests, responses, token usage, latency, and errors, but ensure PII is redacted or never logged. You cannot fix what you cannot see. By internalizing these principles, you are well equipped to manage the complexities of LLM deployments. When you're in a technical interview, especially for a role involving AI or machine learning engineering, you need a concise, impactful statement that demonstrates your grasp of production realities. Here's your one-liner, which encapsulates the essence of this module. I deploy LLM APIs behind rate limiting, caching, and guardrails as non-negotiable production requirements. The Ship It checklist prevents the cost explosion, latency spike, and quality degradation incidents that every team hits without them. This statement immediately signals to your interviewer that you understand the unique challenges of LLM deployments beyond just model training. It shows you're aware of the financial implications, the performance needs, the safety concerns, and the systemic approach required for reliable AI systems. It highlights your proactive mindset in anticipating and mitigating common failure modes. Practicing this one-liner ensures you can articulate your LLMOps expertise clearly and confidently, demonstrating that you're not just a model builder, but a system architect capable of bringing AI safely and efficiently to production. These LLMOps principles aren't just theoretical, they are actively implemented across the industry. Major LLM providers like OpenAI, Anthropic, and Google all offer built-in rate limiting, usage dashboards, and spending caps. These are your first line of defense, but client-side controls are still necessary. For broader solutions, services like Cloudflare AI Gateway act as a proxy, automatically adding caching, rate limiting, and observability to any LLM API call you make, abstracting away much of the complexity. Open source tools like LiteLLM provide a unified interface across 100+ LLM providers, complete with built-in rate limiting and intelligent fallbacks, allowing you to easily switch providers or use multiple models without changing your application code. Similarly, Portkey offers an AI gateway with semantic caching, automatic retries, and provider fallback, essentially acting as a load balancer for LLMs, routing requests intelligently to optimize cost and performance. And if you look at every production chatbot, whether it's Intercom AI, Zendesk AI, or custom support bots, you'll find the core pattern we've discussed: rate limiting followed by caching, then input guardrails, the LLM call, and finally output validation. This pattern is universal because it directly addresses the fundamental challenges of deploying generative AI reliably and responsibly.
These in-the-wild examples confirm that the practices we've learned are industry standards, critical for success. We have reached the culmination of our LLMOps and deployment module. You've learned how to transition your LLM prototypes into resilient, cost-effective, and secure production systems. The key takeaways are clear. Prioritize rate limiting and caching for cost and performance, implement comprehensive input and output guardrails for safety and quality, and always build for reliability with timeouts and fallbacks. Remember the LLM Ship It checklist as your guiding framework for every deployment. Looking ahead, our journey into advanced AI engineering continues. The next module, Evaluation and Monitoring, will build directly upon this foundation. It's not enough to deploy. You must continuously evaluate the performance, quality, and safety of your LLM systems in production and monitor their behavior for drift, hallucinations, or emerging issues. We'll dive deep into metrics, A/B testing, and specialized tools to ensure your deployed AI remains effective and trustworthy over its entire lifecycle. This continuous feedback loop is the final piece of the LLMOps puzzle. Thank you for your dedication, and I look forward to seeing you in the next module as we continue to master the art of building and managing advanced AI applications.